Now, in our previous class, we were discussing with MO of water, how to construct the MO of water molecule, and we have already discussed that in this water molecule, if you consider this as maybe x-axis, suppose this be the z-axis, and perpendicular to the plane of the screen, suppose this be the y-axis. Okay, now we have also discussed that the orbitals which should be involved in the construction of MO for oxygen, it should be 2s, 2px, 2py, 2pz, and the 1s orbitals of the two hydrogen, they will combine in phase and out of phase to form two group orbitals, isn't it? So we have already discussed that these group orbitals, when they are combining in phase, this is the oxygen. So Chi 1s plus Chi 1s of hydrogen, when they are combining in phase, we have named this group orbital as A1. And when they are combining out of phase, we have named them as, this is out of phase combination. This is the position of oxygen. So this is B1. This we have discussed. And we have also mentioned that this 2s orbitals, it can be written as A1, 2pz also as A1, 2px, 2px, this will be B1, and 2py, it will be B2. So we have already discussed this portion. Okay, so A1, B1, so we are using the symmetry notation to represent the orbitals. Now, using this idea, we want to construct the MO energy level diagram for water molecule. So how to do it? See, if you want to construct this MO, suppose this is the energy axis. So this is the energy axis. Suppose this is the 2s of oxygen, and these are the 2p orbitals. Obviously, they are degenerate of oxygen. Now, this 2s orbital, as we have mentioned, this will be A1, and this 2p orbitals, this px, suppose this is 2px we have mentioned as B1, 2py as B2, py as B2, and pz, this is A1. Okay, so these are the 2p orbitals. So these are the atomic orbitals of oxygen. Now, what we have done is we have combined the 1s orbitals of the two hydrogen atoms. Okay, so these are the atomic orbitals of oxygen. Now, for 1s orbital, you have to remember that the energy of 1s orbitals of the two hydrogens, these are the 1s orbitals. Remember, the energy will be above the 2p of oxygen. So since the orbital electronegativity of oxygen is very high, so what happens? The energy, or even the energy of 2p, becomes lesser than that of 1s of hydrogen. Okay, orbital effective nuclear charge is very high. So these 1s orbitals, as we have mentioned, they will combine in phase and out of phase. So when they are combining in phase, we have named this orbital as A1, and when it has combined out of phase, this is B1. Now, if you want to draw the shape of these orbitals, that will be easier for us. So suppose if you want to draw the shape of say 2s orbital, so this 2s orbital is like this, you know already. This is a1 px. So px, we have considered this x-axis. This is px. Py is perpendicular to the plane of the screen. So it's like this, py. It is perpendicular to the plane of the screen, isn't it? This is the x-axis. This is the y-axis, which is perpendicular to the plane of the screen. And pz orbital, it's like this. This is the pz orbital. This is the z-axis. Now regarding this a1, as we have drawn before, this a1, it's like this. Positive, negative, both are in positive phase, same phase. And b1, একটা positive, the other one is negative, position of oxygen. Now we have to combine these orbitals having similar symmetry. Now if you look closely, you'll find that the orbitals, the atomic orbitals, this a1, that means this 2s, a1 from 2pz, and these two, they will combine with a1, this group orbital, a1 group orbital. Okay, so these are the atomic orbitals and these are the group orbitals of the two hydrogen atoms. So these three, that means this a1 from 2s, a1 from 2pz, and a1, this a1 group orbital, they will combine. These three will combine to form three molecular orbitals. Three atomic orbitals, they are combining to form three molecular orbitals. Now whenever there are three molecular orbitals, then one will be bonding, the other will be anti-bonding, and the third one will be non-bonding, will be of non-bonding character. So let us see this 2s, this a1, they are combining. Now we can say this is the bonding molecular orbital, isn't it? Then in a similar way, this will be the anti-bonding molecular orbital. See, it will have very low contribution from this 2s because this is of much higher energy. And also this one, it has very low contribution from this 2pz because you see this is of much lower energy. Okay. Also it has low contribution from a1 also. And the non-bonding orbital, it will be somewhere here, somewhere like this. Sorry. So this non-bonding orbital, it will have contribution from all the three, high contribution from all the three. So this is how we can draw the bonding. Say, let us name it as small a, a1. This is bonding. Okay. And let it be somewhere here. Yes, like this. This is A1. This is a bonding molecular orbital, BMO. So let us name this as maybe 1A1 BMO. Okay. Acha, this is also of A1 symmetry. So this is a ABMO. And this is also of A1 symmetry, obviously. This is a NBMO. non-bonding molecular orbital. Now, if you want to draw the shapes of these orbitals, which is of course beyond the scope of the syllabus, but if you want to draw the shapes of these molecular orbitals, see this, first of all, let it be 1, let it be maybe 3, and say this is maybe 5. 1, 3, let it be 6. Okay. No, 5 equal 6 now, 5. Let it be 5. 1, 3, 5. Now you can name them, the naming of these orbitals, you can name them as you wish. No problem. I am naming it like this. There is some reason for that, you'll understand. So if you want to look at the shape of this orbital 1a1, see 1a1, it has very high contribution from this 2s, and there is in phase combination with a1, isn't it? Since this is a bonding molecular orbital, so there is in phase combination between a1 and primarily 2s. So we can consider the shape somewhat like this. This is 2s, and a1, so it's like this. Both are in similar phase, positive phase আছে ধরো, for example. Okay, so this is the shape of this molecular orbital. Now if you want to look at the shape of this molecular orbital, antibonding molecular orbital. So antibonding molecular orbital means they are combining in out of phase. That means suppose if this is maybe out of phase যদি আমরা ধরি, of course it will have very low contribution from S. So major contribution is from 2pz, 2pz and A1. They are practically combining in out of phase. So what should be the shape? It can be, we can write the shape like this. See, this is 2pz, isn't it? And these are the 1s orbitals. These are the 1s orbitals. 1s orbitals, rather, this is the phi 1, isn't it? Phi 1. Now, if we consider their out of phase combination, so out of phase combination should be like this. See, this is the out of phase. That means this is in the negative phase. We are showing this in the negative phase. That means it's like this. These two are in the positive phase. A positive phase আছে, and this is in the negative phase. So this is how we can say this is an anti-bonding combination. এইটা যদি positive phase থাকতো, this would have been a bonding combination. So this is an anti-bonding combination. Now let us consider the non-bonding combination. Okay, now in this non-bonding molecular orbital, see, it has a greater contribution, obviously. It has greater contribution from A1 and PZ, and there is some combination from 2s also. So if you look at this orbital, this is 2s of oxygen. See, this is 2pz of oxygen, and this is what we have drawn is phi 1, isn't it? And in this non-bonding combination, see why it is non-bonding. See, in this, why it is non-bonding? Because the positive and negative phase, they are combining together. See, this is the positive phase, this is the negative phase. Positive phase in 2s, negative phase in 2pz. So they are combining together. So that's why it's a non-bonding combination. Okay, so this is how we can say it's a non-bonding combination. But it can be written like this also. You can show it like this. See, same thing, this is a non-bonding combination. Now let us move to the combination of this B1. How this B1 will combine with this B1, PX. This B1 of oxygen. The B1, this group orbital, how it will combine with B1, that means PX of oxygen. So this combination we can show it with a different color, maybe with blue. So this B1 and PX, they are combining to form this. These are the two orbitals. They are combining to form a bonding. This one is bonding. Say, suppose this is 2B2 and this is 6B2. Sorry, B1. Very sorry. 2B1 and 6B1. 2B1 and 6B1. So this is the bonding molecular orbital B1 and this is the anti-bonding molecular orbital. Okay. Now if you want to see the shapes of these orbitals, see the px, which of these orbitals are combining? The px is combining with this b1. Now when we are considering in phase combination, look, this is the px and b1 is like this. Of course their phase, if you look at the phase, we need to see for b1 এই আউট অফ ফেজে বি1 মানে কি, একটা পজিটিভ ফেজে আছে একটা নেগেটিভ ফেজে আছে, তাই তো? একটা পজিটিভ একটা নেগেটিভ ফেজে আছে, আমরা শেডেড করে দেখাচ্ছি। আর পি অরবিটাল দেখো, পি এক্স অরবিটালও তাই, পজিটিভ আর নেগেটিভ ফেজ। সো উই ক্যান consider this as in phase combination. This is the x-axis and this is the phi 2. That means b1 okay? Rather this b1, this b1, this is the b1, this b1 portion, it has combined in phase with 2px. So this is how we can draw the group orbital, molecular orbital. This is the group orbital. It is combining with 2px to form this molecular orbital, which is b1, 2b1. If you look at the symmetry, you'll find that this b1 symmetry will be retained. In a similar way, this e1 symmetry is also retained in each of these orbitals. Each of these molecular orbitals, if you look at these molecular orbitals, you'll find that e1 symmetry is retained. Now if you consider this 6b1, the anti-bonding molecular orbital, the combination will be in out of phase. See, this is in phase combination. Then the combination will be in out of phase, isn't it? So how can we draw it? Look carefully. See, this is the px orbital. So this is the px orbital and this is b1, that means formed by out of phase combination, group orbital. Now out of phase means, suppose if we consider the phase of px to be undisturbed as it was in the previous case, that means in this case, then we have to reverse the phase of this orbital, this group orbital, isn't it? So the situation will be like this. So this is out of phase combination. Can you follow this? This is out of phase combination. If this is in phase, see if this is in phase, and if we change the phase of any one of these two orbitals, we have changed the phase of this group orbital. Okay, we have changed the phase. So this is out of phase combination. So this is 6b1, and the rest, if you look at, the only orbital left is, that is b2, which is 2p. This b2 is 2py. 2py has no matching symmetry orbital, so it will remain as non-bonding, and its symmetry will remain as b2. So these are the two non-bonding molecular orbitals. देखो এইটা আর এটা non-bonding molecular orbitals. So this is H2O MO. Okay. Now if you write down the configurations, if you insert the electrons, oxygen হচ্ছে 2s2 2p4, and for the two hydrogen atom it's like this. The configurations in atomic orbitals and group orbitals will be similar. So it's like this. So in total there are 8 electrons. So we have to insert the electrons like this: 1 2 3 4 5 6 7 8, isn't it? So if you look at the HOMO, this is HOMO, this is H minus 1. Now HOMO minus 1, both are non-bonding, both are of non-bonding character, isn't it? So first of all you find out the bond order. See, bond order, this is total number of bonding electrons. These are the two bonding electrons, rather 4 bonding electrons. So 4 minus 0 by 2, so this is 2.0, and this is in keeping with the formation of 2 bonds, isn't it? So that's why bond order is 2.0. Now normally, as you know, that these electrons in the non-bonding orbitals, these pair of electrons in non-bonding molecular orbitals, they behave as lone pairs, isn't it? They behave as lone pairs. So we can say these are lone pairs, and if you look at these orbitals, this 3a1, first of all, this 3a1, it has greater contribution from which side? It has greater contribution from the oxygen side. So since it has greater contribution from the oxygen side, so naturally we can say that this pair of electron is over oxygen. So this pair of electron is over oxygen, so we can say that there is a lone pair, this lone pair over oxygen. This is contributed by this is present rather in 3a1, this lone pair over oxygen. And in a similar way, if you look at b2, the other non-bonding orbital, see, the other non-bonding orbital, it has practically full contribution from the oxygen side. So naturally this pair of electron, this is also over oxygen. So so there is another lone pair. So these lone pairs, এটাকে আমরা 4b2 লিখি. So this can be, say, 3a1 and this 4b2 in terms of molecular orbital. But you can well understand that these lone pairs, they are not equivalent, isn't it? The two lone pairs over water, They are not equivalent because you see this is of higher energy, isn't it? And its symmetry is also different. So since it is of higher energy, usually during chemical reaction, that means say when water is participating in chemical reactions where say lone pair has to be donated. Okay, so this lone pair, only one lone pair is donated. I mean, during chemical reaction, the lone pair which is donated is from the HOMO. Okay, that means HOMO means this one 4B2. So it is donated from 4B2. Okay, this is 4B2. It is donated from 4B2. So that is why when water behaves as a Lewis base, okay, when water behaves as a Lewis base, it is donating only one pair of electron, that is from the HOMO. And this pair of electron, which is also non-bonding, this is what? This is 3A1. This pair of electron, this is also non-bonding, this 3A1. Now this pair of electron is normally not donated during chemical reaction. But both the lone pairs may be involved in hydrogen bonding. Okay, during the formation of hydrogen bonds, probably you know that both the lone pairs, they are involved. Both the lone pairs, they are involved during the formation of hydrogen bond. So it's like this. So in this way, in water molecule, probably it is known to you, in this way, each of these water molecules, they can participate in the formation of four hydrogen bonds, isn't it? If you look at a water molecule, you'll find that it is participating in four hydrogen bonds. So both the lone pairs, they are involved in the formation of hydrogen bonds. Okay.